If you stood on the Martian surface and watched the sky, Phobos would rise in the wrong direction. Not east, where every other moon in the solar system rises from the perspective of an observer standing on the planet's surface. West, Phobos rises in the west and moves across the Martian sky in approximately 4 hours before setting in the east. Completing this backward transit not once, but nearly 3 times per Martian day, racing so fast across the sky that its motion against the background stars is visible in real time. During each of its transits, Phobos appears to an observer on Mars as a small, irregular disk, about 1/3 the angular diameter of Earth's moon as seen from Earth. It is big enough to resolve as a disk rather than a point, but small enough to fit several times across the face of the Sun during the partial eclipses it causes. Eclipses that are closer to transits than to the totality covering eclipses the Moon produces on Earth. The reason for this backward motion is simple in its statement and extraordinary in its implication. Phobos orbits Mars in 7 hours and 39 minutes. Mars rotates in approximately 24 hours and 37 minutes, a Martian day nearly identical in length to an Earth day. Phobos completes a full orbit faster than Mars completes one rotation. It therefore moves around Mars faster than the surface moves beneath it, overtaking the rotation, appearing to travel backward across the sky in the same way that a faster car on the highway appears to move forward relative to you even as both vehicles travel in the same direction. This makes Phobos unique among large moons. It is the only one in the solar system that orbits faster than its planet rotates. This is not a curiosity. It is the signature of a moon in an unstable position, a moon that, by the physics of orbital mechanics, cannot stay where it is indefinitely. Phobos is falling. Not dramatically, not visibly from one year to the next. It loses approximately 1.8 centimeters of orbital altitude per year as tidal interactions with Mars gradually drain energy from its orbit and pull it inward. At this rate, in approximately 30 to 50 million years, far shorter than the dinosaurs' reign on Earth, Phobos will either break apart into a ring of debris or, if it holds together long enough, collide with the Martian surface. The timeline is already set. The physics is already running. And the reason Phobos is in this position, orbiting faster than its planet rotates, so close to Mars's surface, apparently composed of material that doesn't match any known category of object particularly well, is a question that planetary scientists cannot fully answer despite more than a century of observation and decades of dedicated spacecraft study. This briefing covers what Phobos is, what the measurements show and don't show, what the competing explanations require, and what the orbital clock tells us about one of the most anomalous objects in the solar system. If this is the kind of briefing you want more of, hit subscribe and stay with me. The mission begins now. Open the Discovery file. Phobos and Deimos, the 2 moons of Mars, were predicted to exist before they were found, but for a reason that reflects the intellectual peculiarities of their era rather than any physical insight. Johannes Kepler, in the early 17th century, noted that Earth has 1 moon, Jupiter had 4, and Mars lay between them. By some reasoning about mathematical progression, he expected Mars to have 2 moons. Jonathan Swift, in Gulliver's Travels, published in 1726, described fictional Martian astronomers who had discovered 2 moons of Mars with specific orbital periods. This literary prediction preceded the actual discovery by 151 years, a coincidence that has attracted disproportionate attention in popular writing. but which reflects guessing rather than any genuine scientific prescience. The actual discovery came from systematic, sustained searching by Asaph Hall at the U.S. Naval Observatory in Washington, D.C., during Mars's close approach to Earth in August 1877. He was using the observatory's 26-inch refractor, then the largest operational refracting telescope in the world, scanning systematically near Mars. He found nothing for days. By his own account in papers he wrote after the discovery, he was considering abandoning the search. His wife, Angelina Stickney Hall, encouraged him to continue. On August 11, 1877, Hall detected something near Mars. On August 17, he detected the outer moon, and on August 18, he confirmed both objects and announced the discovery. The moons were named for the sons of Ares in Greek mythology, Deimos and Phobos. From the moment of discovery, Phobos presented anomalies. Its orbital period, immediately evident from the motion of the point of light around Mars over several nights, was clearly very short. Hall computed the orbital radius and found it extraordinarily close to the planet's surface. For comparison, the Moon orbits Earth at roughly 60 times Earth's radius. Phobos orbits Mars at only about 2.8 times Mars's radius. This proximity immediately raised questions that have not been fully answered in the 148 years since Hall first recorded that Phobos was there. Scan the orbital mechanics file. Phobos's current orbital situation is not simply unusual. It is physically inconsistent with long-term stability, and understanding why requires understanding the role of synchronous orbit in planetary moon systems. Every rotating planet has a specific orbital radius at which an orbiting object would complete one orbit in exactly the time the planet takes to complete one rotation. This is called the synchronous orbit radius. Earth's synchronous orbit is at approximately 42,000 kilometers from Earth's center, the altitude at which geostationary satellites sit, maintaining a fixed position above a point on Earth's surface because they move in exact synchrony with the ground below. For Mars, the synchronous orbit radius is approximately 20,400 kilometers from Mars's center. Any moon orbiting outside this radius orbits more slowly than Mars rotates. Any moon orbiting inside this radius orbits faster than Mars rotates. Phobos, with its orbital radius of approximately 9,376 kilometers from Mars's center, is well inside the synchronous orbit radius by a factor of roughly 2. This position has a consequence determined by the physics of tidal interaction. A moon orbiting outside the synchronous radius bulges the planet's surface toward it gravitationally, and Mars's rotation carries this tidal bulge slightly ahead of the moon's position. The gravitational interaction between the leading bulge and the moon pulls the moon forward in its orbit, adding energy to the moon and gradually increasing its orbital radius. This is why the moon is slowly receding from Earth. Earth's rotation is faster than the moon's orbital period, so the tidal bulge leads the moon and adds energy to the orbit, pushing the moon outward at about 3.8 centimeters per year. For Phobos, the situation is precisely reversed. Phobos orbits inside the synchronous radius, moving faster than Mars rotates. The tidal bulge, raised by Phobos, lags behind Phobos's position rather than leading it. The gravitational interaction between the lagging bulge and Phobos pulls Phobos backward in its orbit, removing energy and reducing the orbital radius. Phobos, as a consequence, is spiraling inward at approximately 1.8 centimeters per year. This is not a controversial measurement. Multiple spacecraft, including Viking 1 and 2, Mars Global Surveyor, and Mars Express, have measured Phobos's orbital evolution with sufficient precision to confirm the decay rate. The rate is consistent with what would be expected from tidal friction given Mars's internal structure and Phobos's mass. The orbital decay is real, confirmed, and ongoing. The endpoint of the decay depends on whether Phobos remains structurally intact as it spirals inward. A moon approaching too close to its parent planet experiences increasing tidal stress. The difference in gravitational pull between the moon's near side and far side becomes large enough to exceed the moon's structural strength. The distance at which this occurs is called the Roche limit. For Phobos and Mars, the Roche limit is estimated at approximately 7,200 to 8,300 kilometers from Mars's center, depending on assumptions about Phobos's internal structure. Phobos currently orbits at approximately 9,376 kilometers from Mars's center and is falling at approximately 1.8 centimeters per year. At this rate, Phobos will reach the Roche limit in approximately 30 to 50 million years. If it survives structurally until that point, it will begin to break apart, with the outer portions disrupted into a ring of debris circling Mars, while the inner core, if it has one, might continue spiraling toward the surface. If the structural integrity fails before the Roche limit is reached, it may disintegrate earlier. The timescales are estimates with significant uncertainty. The exact rate of orbital decay depends on Mars's tidal dissipation factor, which is not precisely known, but the direction and the approximate scale are not in question. Phobos's current orbital situation is not simply unusual. It is physically inconsistent with long-term stability, and understanding why requires understanding the role of synchronous orbit in planetary moon systems. Every rotating planet has a specific orbital radius at which an orbiting object would complete one orbit in exactly the time the planet takes to complete one rotation. This is called the synchronous orbit radius. Earth's synchronous orbit is at approximately 42,000 kilometers from Earth's center. The altitude at which geostationary satellites sit, maintaining a fixed position above a point on Earth's surface because they orbit in exact synchrony with the ground below. From the surface of Earth, a geostationary satellite never appears to move against the sky. For Mars, the synchronous orbit radius is approximately 20,400 kilometers from Mars's center. Any moon orbiting outside this radius orbits more slowly than Mars rotates. Any moon orbiting inside this radius orbits faster than Mars rotates. Phobos, with its orbital radius of approximately 9,376 kilometers from Mars's center, is well inside the synchronous orbit radius by a factor of roughly 2. This position has a consequence determined by the physics of tidal interaction. A moon orbiting outside the synchronous radius raises a tidal bulge on the planet that is carried slightly ahead of the moon's position by the planet's faster rotation. The gravitational interaction between the leading bulge and the moon accelerates the moon in its orbit, adding energy and increasing the orbital radius over time. This is precisely the situation for Earth's moon. Earth's rotation is faster than the moon's orbital period. The tidal bulge leads the moon, and the moon is receding from Earth at approximately 3.8 centimeters per year. For Phobos, the situation is precisely reversed. Phobos orbits inside the synchronous radius, moving faster than Mars rotates. The tidal bulge raised by Phobos lags behind Phobos's current position rather than leading it. The gravitational interaction between the lagging bulge and Phobos retards Phobos in its orbit, removing energy and reducing the orbital radius. Phobos spirals inward at approximately 1.8 centimeters per year. Multiple Mars spacecraft have measured Phobos's orbit with sufficient precision to confirm this decay rate. Mars Express has been particularly valuable. The spacecraft has executed more than 100 targeted close flybys of Phobos, some approaching within 67 kilometers of the surface, generating measurements of Phobos's gravitational field that constrain both its mass and the orbital decay. The consistency between measurements from different missions over decades of observation, Viking, Mars Global Surveyor, and Mars Express, gives the orbital decay measurement a robustness that's not possible to dispute on observational grounds. The endpoint of the decay depends on Phobos's structural integrity. As Phobos spirals inward, the differential gravitational force across its diameter. The difference between the gravitational pull of Mars on Phobos's near side versus its far side increases at the Roche limit. This differential force equals the gravitational cohesion binding Phobos together. For a body with no internal strength, a fluid or a very weak rubble pile, disruption begins at the fluid Roche limit, approximately 9,400 kilometers from Mars's center. This is almost exactly Phobos's current orbital radius. For a body with real internal strength, the effective Roche limit is inside this, roughly 7,200 to 8,300 kilometers from Mars's center. Phobos, with its high porosity suggesting a rubble pile structure, is somewhere between these two limits. The fact that it hasn't already disrupted, despite being near the fluid Roche limit, implies that it has some structural cohesion, but how much, and therefore exactly when it will disrupt, is connected to the unresolved question of its internal structure. If it's a loose rubble pile, disruption may occur somewhat earlier than 30 million years from now. If it has more structural integrity than the density implies, it may survive longer, reaching the inner Roche limit and beginning to shed material only around the 50 million year mark. In either case, a ring of Phobos debris circling Mars is, in geological terms, a near-future event. Astronomers observing Mars from Earth tens of millions of years from now, assuming any observers then exist, will see a ringed Mars. Pull up the density anomaly file. Phobos's size can be measured from spacecraft images. Multiple Mars orbiters have imaged Phobos in detail, and from those images, combined with careful measurement of the viewing geometry, the shape and volume of Phobos have been established. Phobos is not a sphere, it is an irregular, somewhat elongated body approximately 27 kilometers along its longest axis, 22 kilometers in the intermediate direction, and 18 kilometers along the shortest axis. Its volume is approximately 5,700 cubic kilometers. Phobos's mass can be measured from the gravitational influence it exerts on spacecraft that fly close to it. Mars Express has executed multiple targeted close flybys of Phobos, approaching as close as 67 kilometers from the surface, so close that the camera blur is measurable. These flybys allowed precise measurement of the gravitational pull Phobos exerts on the spacecraft, and from this, its mass was determined. Dividing the measured mass by the measured volume gives Phobos's density approximately 1.876 grams per cubic centimeter. This number is low. Ordinary rocky material, the stuff that makes up asteroids, planetary crusts, and meteorites, has densities ranging from approximately 2.5 to 3.5 grams per cubic centimeter for the most common types. Phobos's density of approximately 1.9 grams per cubic centimeter is significantly below this range. For comparison, liquid water has a density of 1.0 grams per cubic centimeter. The low density implies one of two things. Either Phobos is composed of material that is intrinsically less dense than rock, such as ice mixed with rock, or Phobos is compositionally rock-like but has a large fraction of its volume occupied by empty space, voids, cracks, and gaps within its interior, making it more porous than a solid rock. Phobos's surface reflectance spectrum argues against significant ice content. The spectral properties of Phobos's surface, how it reflects light at different wavelengths, resemble dark, carbonaceous material similar to D-type or C-type asteroids, not icy bodies. Water ice has distinctive spectral signatures that Phobos does not show. The alternative, high porosity, would make Phobos a rubble pile, a loosely consolidated collection of rock fragments held together by gravity rather than structural cohesion, with substantial empty space between the fragments. Estimates of the fraction of empty space required to account for the density range from approximately 25 to 35%. This is high, comparable to or exceeding the porosity of the most porous known small bodies in the solar system. A note on terminology is worth making here, because the word hollow has appeared in popular discussions of Phobos's density and is an overstatement of what the measurements indicate. In 1959 and 1960, the Soviet astrophysicist Iosif Shklovsky argued that Phobos might be hollow, artificially so, in fact, based on orbital decay measurements that seemed at the time to be faster than tidal friction could explain. His interpretation was that the anomalously fast decay implied an object with very low density, which he took to imply an artificial hollow shell. Subsequent measurements showed that the decay rate was actually consistent with a solid but very porous natural body, and Shklovsky's specific argument was abandoned in the scientific community, though the hollow moon framing has persisted in popular coverage. What the measurements actually indicate is high porosity, not hollowness in the sense of an empty interior. Open the origin mystery file. Where did Phobos come from? This question has three broad candidate answers, each with specific supporting evidence and specific problems that prevent any of them from being accepted as confirmed. The first hypothesis is that Phobos is a captured asteroid, an object from the asteroid belt or the outer solar system that wandered too close to Mars and was captured into Mars' orbit. This hypothesis has an obvious appeal. Phobos's dark carbonaceous surface spectrum resembles D-type or T-type asteroids found in the outer asteroid belt and among the Trojan asteroids at Jupiter's Lagrange points. The surface composition, such as it can be determined from spectroscopy, is at least roughly consistent with the kind of primitive, carbon-rich material that outer asteroid belt bodies are made of. The problem with capture is orbital mechanics. Objects captured by a planet's gravity from unbound trajectories enter highly elliptical inclined orbits. They don't enter nearly circular, nearly equatorial orbits like Phobos occupies, circularizing and de-inclining an initially eccentric. Tilted capture orbit requires removing a very large amount of energy and angular momentum from the captured object, and the mechanisms available to do this, atmospheric drag, interactions with a primordial disk of material around Mars, or multi-body gravitational interactions, are all either insufficient in magnitude or unavailable at the right time. Extensive modeling has consistently found it difficult to explain how a captured asteroid ends up where Phobos is. The second hypothesis is that Phobos formed in place, assembled from a disk of material that orbited Mars early in its history, possibly generated by a large impact into Mars, similar to the impact thought to have produced Earth's moon. In this scenario, Phobos and Deimos both formed from this disk, explaining their nearly circular and nearly equatorial orbits naturally. The equatorial, low-inclination orbits are what any debris disk orbiting Mars would naturally produce, and formation from such a disk makes the orbital configuration easy to explain. The problem with in situ formation from a disk is compositional. If Phobos formed from debris ejected from Mars by a giant impact, it should be made of Martian material. The composition of Mars is reasonably well constrained from measurements of the Martian crust and from meteorites of Martian origin found on Earth. Phobos's spectral reflectance does not clearly match Martian crustal material, and some analyses have found that its spectrum is more consistent with outer asteroid belt material than with anything specifically Martian. This discrepancy is not fatal to the impact origin hypothesis. The impact could have incorporated material from the impactor rather than just Mars, or the surface of Phobos could have been altered by space weathering in ways that change the spectrum from its original composition. But the discrepancy remains a genuine challenge that supporters of the impact origin hypothesis have to address. The third hypothesis involves Phobos forming from a disk generated not by a single giant impact, but by the cumulative effects of multiple smaller impacts over early Mars's history. This scenario produces a disk with a different composition than the single giant impact scenario and may address some of the compositional issues. But it introduces its own challenges about whether the right amount of material can be delivered to the right orbits by this mechanism. A fourth, less discussed possibility is that Phobos and Deimos are remnants of a larger moon system that existed early in Mars's history and was subsequently disrupted, with Phobos and Deimos being the survivors of a more extensive moonlet population. No hypothesis currently explains all of the available observations. The orbital configuration points toward in situ formation. The surface composition points away from it. The density and porosity fit neither category cleanly. The origin of Phobos is a genuinely open question, and it will remain open until the Martian moon's exploration mission returns physical samples from Phobos' surface that can be directly analyzed in terrestrial laboratories. Open the composition file. What Phobos is made of should, in principle, resolve the origin debate. In practice, the compositional data introduces as many complications as it resolves. Phobos is dark. Its albedo, the fraction of sunlight it reflects, is approximately 0.07, meaning it reflects only about 7% of the sunlight hitting it and absorbs the rest. This places it among the darkest objects in the solar system, darker than coal. The darkness itself is informative. Dark surfaces in the outer solar system and asteroid belt are typically associated with carbonaceous material, complex organic compounds, and dark minerals like magnetite that absorb visible light efficiently. This puts Phobos in the general category of carbonaceous asteroids rather than the rocky silicate asteroids that make up the inner solar system's most common types. But within this broad category, the spectral classification of Phobos is uncertain. Different analyses of Phobos' reflectance spectrum, measured by the Viking orbiters, by the Phobos 2 spacecraft and by Mars Express, have placed Phobos in different spectral categories. Some analyses classify it as a D-type or T-type asteroid, types found predominantly in the outer main asteroid belt and among the Jupiter Trojans. These types are rare in the inner solar system and are interpreted as primitive objects that haven't been altered by heating, making them compositionally ancient. Others have found that Phobos' spectrum resembles certain types of dark carbonaceous meteorites called Tagish lake-type meteorites or anhydrous carbonaceous material. Neither of these categories maps cleanly onto either of the main origin hypotheses. If Phobos is D-type, that's somewhat consistent with a captured outer asteroid belt body, but the orbital mechanics problem of capture remains. If Phobos has a composition similar to carbonaceous chondrites found in the inner asteroid belt, that's less consistent with capture from the outer belt, but still doesn't specifically implicate Martian origin. The comparison with Martian material is the most critical test for the impact origin hypothesis. Mars's surface and meteorite samples from Mars have specific oxygen isotope ratios and elemental compositions that differ distinctly from those of carbonaceous chondrites. If Phobos formed from Martian debris, its composition should broadly match Martian material, and specifically its oxygen isotope ratios should fall along the Martian fractionation line in isotope ratio space. The available spectral data cannot determine oxygen isotope ratios that requires physical samples in a laboratory. What the spectral data show is a surface that does not particularly resemble the spectral signature of Martian dust or basaltic rock. This is a point against the impact origin, but not a definitive one, because the surface of Phobos has been altered by billions of years of space weathering, bombardment by micrometeorites and solar wind particles that changes spectral properties independently of the original composition. Space weathering darkens and neutralizes spectra, potentially making material of Martian origin look more like carbonaceous asteroid material in spectral terms. The compositional question, like the origin question as a whole, points toward the necessity of sample return. The spectral data available from remote sensing cannot distinguish between the hypotheses with the required precision. The oxygen isotope ratios in physical samples can. One additional compositional clue: observations of Phobos in the mid-infrared by the Mars Reconnaissance Orbiter's XRISM instrument and the European Mars Express mission's Omega spectrometer have detected a spectral feature associated with phyllosilicates, clay minerals, in some regions of Phobos' surface. Phyllosilicates form through water-rock interaction at moderate temperatures. Their presence on Phobos' surface implies that the material was, at some point in its history, in contact with liquid water. This could be consistent with either an origin in the outer asteroid belt or with material from early wet Mars. It is not diagnostic in itself, but it adds another layer to the compositional puzzle that no single origin hypothesis accommodates cleanly. Read the grooves file. Phobos' surface is crossed by a system of parallel grooves and striations that have been visible since the Viking orbiter images of the late 1970s, and that remain one of the most visually striking and poorly explained features of any body in the solar system. The grooves are not a single feature. They are a system, hundreds of roughly parallel furrows and troughs, typically 100 to 200 meters wide and 10 to 30 meters deep, running in subparallel bands across large portions of Phobos' surface. Some are straight over hundreds of kilometers. Some curve gently, They can be seen in high-resolution Mars Express and Mars Reconnaissance Orbiter images as a family of marks that look, superficially, like something has scored Phobos' surface with parallel lines. A scratching or tearing pattern that suggests a directional process rather than random impacts or volcanic events. The explanation that dominated early discussions was ejecta from the formation of Stickney crater, the largest impact feature on Phobos, a crater approximately 9 kilometers across that sits near one end of the elongated moon. The Stickney impact was an event of extraordinary violence relative to Phobos' size. The impactor that created a 9-kilometer crater on a 27-kilometer long moon very nearly destroyed it. Material blasted outward from Stickney could have scoured the surface in patterns consistent with the observed grooves, and many of the grooves do appear to originate from the general vicinity of Stickney. But the Stickney ejecta hypothesis faces specific difficulties. Some grooves appear to originate not from Stickney itself, but from other locations. The grooves in some regions are better described by source points elsewhere on Phobos, and some analysis have found that the geometry of specific groove families doesn't match what would be expected from radially directed ejecta from Stickney. A variant of this hypothesis, that chains of impacts from secondary ejecta, bouncing and rolling across Phobos' surface, carved the grooves, has been more formally modeled, with some supporting evidence from the correspondence between certain groove orientations and the expected trajectories of rolling boulders after the Stickney impact. The hypothesis that has gained significant traction in more recent work involves tidal stress. Phobos is inside Mars's Roche limit for a strengthless fluid body, meaning Mars's differential gravitational pull across Phobos' diameter is sufficient to pull it apart if the moon lacks internal strength. The actual Roche limit for Phobos, accounting for its real internal strength, is somewhat smaller than the fluid Roche limit, and Phobos is not yet being disrupted, but it is experiencing increasing tidal stress as it spirals inward. A 2015 study by Terry Herford and colleagues at NASA's Goddard Space Flight Center modeled the tidal stresses Phobos experiences from Mars and found that the predicted patterns of stress on Phobos' surface, where the tension would concentrate, what orientations the resulting fractures would take, matched the observed groove system closely in many regions. In this interpretation, the grooves are not scars from the Stickney impact, but early-stage fractures developing as Phobos gradually tears itself apart under Mars's increasing tidal pull. They are, in Herford's interpretation, the beginning of the disruption process that will eventually, in tens of millions of years, turn Phobos into a ring. If this interpretation is correct, the grooves are not a record of Phobos' past. They are a preview of its future. The tidal stress hypothesis and the Stickney ejecta hypothesis are not necessarily mutually exclusive. The surface could have been grooved by ejecta from the ancient Stickney impact and also show more recent tidal fracturing. But sorting out which grooves are which and testing the tidal stress hypothesis against the complete groove catalog requires higher resolution surface mapping and subsurface sounding than any mission has yet delivered. Open the Stickney file. Stickney crater deserves specific attention not merely because of its role in groove formation hypotheses, but because of what its existence tells us about Phobos' history and how close Phobos came to not existing in its current form. A crater 9 kilometers in diameter on a moon 27 kilometers in its longest dimension represents an impact of extraordinary relative scale. To match this proportionally on Earth's moon, the crater would need to be over 100 kilometers across, larger than any single impact basin on the Moon's near side. The impactor that created Stickney delivered enough kinetic energy that numerical simulations of the event consistently find Phobos on the edge of complete disruption. The resulting impact shock waves propagated through Phobos's entire interior, fracturing rock throughout the body. High-resolution models of this event find that the fracturing was severe enough to significantly increase bulk porosity to effectively turn a more coherent rocky body into the rubble pile that the density measurements imply. The Stickney impact may therefore be the direct cause of Phobos's anomalous density rather than an incidental feature of a body that was always porous. This connection makes Phobos easier to understand in one respect, rather than requiring an initial formation process that produces an intrinsically porous, low-density body. The standard models can produce an ordinary small rocky body of any origin and then shatter it internally with the Stickney impact to produce the current configuration. The porosity is not primordial. It is the preserved signature of catastrophic internal fracturing. The Stickney crater itself, imaged in detail by Mars Express with approaches as close as 67 kilometers, shows a complex floor structure including a central pit and extensive fractured wall deposits. The ejecta from Stickney blankets much of the hemisphere facing away from Phobos's motion, visible as bright streaks and rays extending from the crater. Some of the grooves radiating from or near Stickney in the images correspond to directions consistent with ejecta trajectories from the impact. The crater and its aftermath are the most visually prominent record of an event that very nearly ended Phobos's existence as a coherent object 4 billion years or more before it falls naturally into Mars. Scan the MMX mission file. Scan the MMX mission file. The question of Phobos's origin, the one question whose answer would resolve or at least significantly constrain all the debates about what Phobos is, can, in principle, be answered by a relatively simple observation. A physical sample of Phobos's surface material, returned to an Earth laboratory and analyzed with modern techniques, would provide the compositional fingerprint that unambiguously distinguishes between Martian-derived material and asteroid-derived material. The Japan Aerospace Exploration Agency's Martian Moons Exploration Mission, known as MMX, is designed specifically to do this. The mission carries a sample collection system and a return capsule and plans to land on Phobos' surface, collect samples, and return them to Earth in the early 2030s if the mission proceeds on schedule. If the returned samples show Martian isotopic ratios, specifically the oxygen isotope ratios that distinguish Martian material from asteroid belt material with high precision, the giant impact origin hypothesis gains strong support, and the capture hypothesis is essentially eliminated. If the samples show isotopic ratios characteristic of outer asteroid belt material, the capture hypothesis is supported, and the formation in place hypotheses require revision. This is the specific test that decades of remote sensing cannot perform. The oxygen isotope ratios of Phobos's surface material would, in essentially all models, differ between Martian-derived material and captured asteroidal material at levels easily measurable in terrestrial mass spectrometers. A few hundred milligrams of Phobos surface material would be sufficient to determine Phobos's origin with high confidence. Until those samples arrive, the origin debate continues to turn on remote sensing observations whose interpretation is model-dependent, orbital dynamics arguments that are powerful but not definitive, and the specific pattern of evidence this briefing has laid out, an orbit that suggests in situ formation, a spectrum that doesn't clearly confirm it, a density that needs explaining, and grooves that point either toward the past or the future, depending on which hypothesis is correct. Close the mission briefing. Pull out the final report. The question this investigation addressed: what specifically is anomalous about Phobos, and what do the available data and the available explanations actually establish? Here is what the evidence confirms. Phobos orbits Mars at approximately 9,376 kilometers from Mars's center in a nearly circular, nearly equatorial orbit with a period of 7 hours and 39 minutes, less than 1/3 of Mars's rotation period, making Phobos the only large moon in the solar system that orbits faster than its planet rotates. Its orbit is decaying at approximately 1.8 centimeters per year due to tidal interaction with Mars. The Roche limit for Phobos around Mars is estimated at roughly 7,200 to 8,300 kilometers from Mars's center, placing the current orbit approximately 1,000 to 2,000 kilometers above this limit. In approximately 30 to 50 million years, Phobos will either break apart at or near the Roche limit or, if structurally intact, impact Mars. Phobos' density is approximately 1.876 grams per cubic centimeter, substantially lower than the density of rocky asteroidal material, implying 25 to 35% porosity or void space in its interior. This high porosity is consistent with a rubble pile structure, possibly produced or enhanced by the Stickney impact, which created a crater approximately 9 kilometers in diameter on a moon 27 kilometers across and would have generated severe internal fracturing. The grooves crossing Phobos' surface remain inadequately explained. The Stickney ejecta hypothesis explains many, but not all groove orientations. The tidal stress hypothesis makes specific predictions that match the observed groove patterns in many regions and provides a physical mechanism consistent with Phobos' current orbital situation. The two hypotheses are not mutually exclusive. Here is what the evidence does not resolve. Phobos' origin is genuinely unknown. The capture hypothesis cannot explain Phobos' nearly circular equatorial orbit without mechanisms that are difficult to confirm. The in situ formation hypothesis cannot clearly explain the spectral mismatch between Phobos' surface and known Martian material. No existing model elegantly explains all the observations simultaneously without requiring additional assumptions. The MMX sample return mission, if it succeeds, will provide the compositional data needed to distinguish between the major origin hypotheses. Remote sensing from orbit has reached the limits of what it can contribute to this specific question. Here is where the genuine scientific weight of Phobos resides. Phobos is the most anomalous moon in the solar system by several measures simultaneously. It is in the wrong orbital position for any known formation mechanism to produce cleanly. It has the wrong density for its apparent composition. Its surface is scarred by marks that either record an ancient near-catastrophic impact, predict a future tidal disruption, or both, and it is falling demonstrably, measurably, irreversibly toward a collision or disintegration that will occur within geological timescales short enough to place it within the remaining lifespan of complex life on Earth. The timeline is set. In 30 to 50 million years, something spectacular will happen near Mars. Either an object breaking apart under tidal forces, spreading a ring of debris around the planet visible from Earth with a modest telescope, or a moon striking a planetary surface with an energy that dwarfs any impact in recorded human history. Which of these outcomes occurs depends on Phobos' internal structure, specifically on whether the rubble pile holds together or shatters as it crosses the Roche limit, and the internal structure is currently unknown. What Phobos' existence tells us about the formation of planetary systems, about the delivery of material to the inner solar system, and about the ultimate fate of planetary satellites that find themselves inside their planet's synchronous orbit. All of this awaits the sample return and the continued analysis of data that spacecraft have been collecting since Viking first photographed those anomalous grooves more than 4 decades ago. The mission brief ends here. Phobos is still rising in the west, still moving across the Martian sky in 4 hours, still spiraling inward at 1.8 centimeters per year. The grooves are still there, still unexplained, still being scored by tidal force or ancient ejecta or both across the surface of a moon that the physics of orbital mechanics has already marked for eventual destruction. What it is and where it came from are questions with answers. The answers are in the rocks. The rocks are 9,376 kilometers above the Martian surface, waiting